Hello friends, myself Dr. Nandakumar Ravale from College of Engineering Ambazogai is going to deal with numerical methods in mechanical engineering. In previous lecture, we have discussed approximate error, true error, relative error, round of error and truncation error. Now today we are going to discuss Taylor's theorem, Taylor series, Taylor's approximation polynomial, error propagation, functions of single variable. Now the Taylor's theorem is nothing but if a function f and its first n plus 1 derivatives are continuous on an interval containing a and x, then the value of function f of x is given by the function as we have seen here. If the function f is a continuous function and it is having n plus 1 derivatives which is continuous in an interval containing a and x, then the value of function f of x is given by f of x is equal to f of a plus f dash of a into x minus a plus f double dash of a divided by 2 factorial into x minus a square plus f triple dash of a divided by 3 factorial into x minus a to the power of 3 plus so on plus fn of a divided by n factorial x minus a to the power of n plus of Rn. So if the function f and its first n plus 1 derivatives are continuous on an interval containing a and x, between a and x, then the value of function f of x is given by this Taylor's theorem, where the remainder Rn, so this term Rn is the remainder, which is given by remainder Rn is equal to integration a to x minus t to the power of n divided by n factorial f of n plus 1 of t dt. So this is the Taylor's theorem, where f dash of a, f double dash of a, f triple dash of a and so on, f n of a are the derivatives of function at the point a. So now this is about the Taylor's theorem. Now the Taylor series, provides a means to predict the function value at a point in terms of function value and its derivatives at another point. So here Taylor series provides a means to predict function value at a point in terms of the function value and its derivative at another point. What does it mean? Taylor's series provides a means to predict function value at a point in terms of the function value and its derivatives at another point. Say for example, f of x is equal to x square plus 2x plus 1. So now this helps us. Say for example, at x is equal to 1, we know f of 1 value will be 1 plus 2 plus 1, it is 4. So if we know f of 1 is equal to 4, by knowing this f of 1 which is 4, if you want to find out f of 1.5 without knowing this original function, you can find this function value that is in terms of derivatives of this function. You know this first value f of 1 is 4 and you don't know this expression polynomial, and you know its derivatives f dash of x, f double dash of x, and so on. If you know derivatives, then you can find out function value at x is equal to 1.5. that is nothing but at another point in terms of derivatives, it gives us the function value. Now say for example, if we draw a graph, we know the function value at point I. Function value is something here, or xi. Say at xi function value is f of xi. This is known to us. And if we know another variable xi plus 1 which is very close, xi plus 1 is very close to xi, then function value f of xi plus 1 can be known. So Taylor series is built in terms by terms. So this Taylor series is built term by term. Is built term by term. Therefore, the function value f of xi plus 1 is approximately very close to f of xi. That is nothing but, say for example, we know f of 1 is equal to 4 for this given function. So for this given function f of x, we know f of 1 is equal to 4. And if we want to find out f of 1.0001, then the answer will be very, very close to 4, because this value of x is very close to each other, that is 1 and 1.001 are very close, 1 and 1.0001 are very close to each other. Therefore the function value f of 1 and function value f of 1.001 will be very close to each other. So that is nothing but this is f of 1.001 we can say, and this is f of 1 are very close to each other. So this we call as equation number 1. This relationship is called the zero order approximation, called as the zero order approximation. Indicates that this indicates that the value of f means function f at a new point is same as the value at old point. This is possible when this is possible, that is f of xi plus 1 is approximately equal to f of xi, when it is possible if xi plus 1 is very close or approximately equal to xi, then only it is possible. This is possible if xi and xi plus 1 are very close to each other. Otherwise this is not true. It is likely that the new value is probably similar to old value. It is likely that the new value is probably similar to old value. If this function if the function changes over an interval additional terms of Taylor series are required. So here we have seen only one term, but now additional terms are required to provide a better estimate. It means xi plus 1 and xi, if are very close to each other, then zero order polynomial will help us to predict the approximate value or next value of f of x at xi plus 1. But if xi plus 1 and xi are not close to each other, if these two terms are not close to each other, then we need to consider other terms of Taylor series. In zeroth order we have considered first term only, but if the difference between these two values of input are different, then the other terms of Taylor series have to be considered. The first order approximation is developed first order approximation is developed by adding another term and second order and so on. See here, the first order polynomial we write here as f of xi plus 1 is equal to f of xi. So this was at zeroth order. To get first order polynomial, we write it as f dash of xi plus of xi plus 1 minus of xi. We call this as equation number 2. This equation number 2 is a first order polynomial of Taylor series. First order Taylor series. Then to get second order, again xi plus 1 f of xi plus 1 is approximately equal to f of xi plus f dash of xi plus 1 minus of xi. This is first order. Adding to this, f double dash of xi divided by 2 factorial xi plus 1 minus xi square. We call this as third equation, which is second order polynomial. And so on. F of xi plus 1 is equal to f of xi plus f dash of xi into xi plus 1 minus of xi plus f double dash of xi divided by 2 factorial xi plus 1 minus of xi square plus of f triple dash of xi divided by 3 factorial xi plus 1 minus of xi to the power of 3 plus plus fn of xi divided by n factorial into xi plus 1 minus of xi to the power of n plus of Rn. So say this is equation number 4. We call this as nth order. This we call as a nth order. Nth order Taylor's polynomial. Or Taylor series, where this Rn is known as a remainder term. So to compensate with the error, this remainder is added, and this compensates the error in this. The remainder term is included to account for all terms from n plus 1 to infinity. So this remainder term Rn is given by f of n plus 1 zeta divided by n plus 1 factorial xi plus 1 minus of xi to the power of n plus 1. So this is equation number 5. This gives us the remainder term, the subscript n, the subscript n subscript n denotes that the remainder term for nth order approximation zeta is the value of x. X that lies between xi and xi plus 1. Now here we define the step size. Defining the step size, h is equal to xi plus 1 minus of xi. So this is the step size. We write this Taylor series polynomial as f of xi plus 1 is equal to f of xi plus of f dash of xi into, there was xi plus 1 minus of xi, in place of xi plus 1 minus of xi, here we write h. So because h we have taken as xi plus 1 minus of xi, so here we take it as h plus of f double dash of xi h divided by 2 factorial plus f triple dash of xi h divided by 3 factorial plus so on plus fn of xi divided by n factorial into h plus of rn, where rn is the remainder term. So where this is equation number 6 we can call, where the remainder term is now r suffix n is equal to f of n plus 1 of zeta divided by n plus 1 factorial into h to the power of n plus 1. So this is equation number 7. So equation number 6 as well as equation number 4 are known as a Taylor series of nth order. It includes all up to nth order, and at the end a remainder term is added to compensate the values from nth order to infinity. Now we see Taylor series approximation of a polynomial with the help of a numerical. So Taylor series approximation of a polynomial. So what he says, say for example this is a numerical problem. Use 0 through 4th order Taylor series expansion to approximate the function. Function is given f of x is equal to minus 0.1 x to the power of 4 minus 0.15 x to the power of 3 minus 0.5 x square minus 0.25 x plus 1.2 from xi is equal to 0 with step value h is equal to 1. That is, predict the function's value at xi plus 1 is equal to 1. So what he says that xi is equal to 0, the xi value is 0, we know. At this xi is equal to 0, if we know the function value will be 1.2. So if you substitute in this function x is equal to 0, the value of function becomes 1.2. So at f of 0, function value is 1.2. He is asking us to find out f of 1. So if you know this polynomial, then it is very easy for us to find out f of 1. But if we do not know this function, without knowing this function, it is very difficult to find out f of 1. That is, at xi plus 1 is equal to 1. So in place of x, if we substitute 1, we will get f of 1 when it is possible if we know this function. If we do not know this function, then it is impossible. But he says that the true value of function at x is equal to 1, that is f of 1, is 0.2. He is giving us the function value f of 1 as 0.2, which is true value. But here we are not substituting x is equal to 1 in this equation directly, and we are not finding f of 1 as 0.2. So we are going to use Taylor series. Now to use Taylor series, we start with the solution. So we know f of 0 is equal to 1.2 because we know this function f of x is equal to minus 0.1 x to the power of 4 minus 0.15 x to the power of 3 minus 0.5 x square minus 0.25 x plus of 1.2. So if you substitute x is equal to 0, so everywhere if you substitute 0, then these first 4 terms become 0 and function value will be 1.2. Now we want to find out this function value f of 1 using Taylor series. So the Taylor series approximation with n is equal to 0. With n is equal to 0 means 0 order Taylor series. If we use 0 order Taylor series, that is f of xi plus 1 means f of 1, so is equal to, function is approximately equal to f of xi. So f of xi is nothing but we know that is 1.2. So here we can say xi is equal to 0 and xi plus 1 is equal to 1. So now we are not substituting xi plus 1 is equal to 1 in this polynomial. We are not substituting this value in this polynomial. What we are doing, we are substituting xi is equal to 0. Then we got this as 1.2. So now we are going to say 0 order equation that we have seen in this slide. 0 order Taylor series of 0 order f of xi plus 1 is equal to f of xi. So here to find out this value of f of 1, we are going to say that f of 1 is equal to f of 0, and f of 0 value we know is 1.2. Now what we know is true value of f of xi plus 1, which is 0.2. So if we substitute here 1 in this equation, we get this as 0.2. So true value of f of xi plus 1, which is known to us. So if we know true value, then we can find out error. The 0 order approximation is constant, and therefore the true error et is equal to, true value is 0.2 and approximate value which we have obtained is 1.2 minus 1.2. So this gives us error of minus 1.0. So now here this is the error. Now for n is equal to 1, so now here it was n is equal to 0, now we take n is equal to 1. So first order, the first derivative must be determined and evaluated at xi. So the first derivative of function must be determined and evaluated at xi is equal to 0. So first derivative of this f of x function f of x, that is f dash of x, will be minus 0.4 x to the power of 3 minus 0.45 x square minus 1.0 x minus 0.25. so this is first derivative of this function f of x. If we derive obtain derivative, this 4 will come in multiplication with this minus 0.1, so it will be 0.4 minus 0.4. so from 4 if we subtract 1, x to the power of 3 and so on. So derivative of this gives us this function first order derivative. So if you substitute f dash of x in place of x0, so this term becomes 0, this term becomes 0, this term becomes 0, answer will be minus 0.25. this is first derivative. So then to find out first order approximation, therefore the first order approximation is given by f of xi plus 1 is equal to approximately equal to f of xi plus of f dash of xi into h. So f of xi value we know, which is 1.2 plus of f dash of xi, just now we obtained as minus 0.25 and value of h in this problem is 1, which is given. So on simplification we get it as 0.95. f of xi plus 1 is equal to 0.95. so here true error, if we see, true value is 0.2, which is given in the problem, minus of 0.95. so this true error proves to be minus 0.75. So this is true error if we consider first order approximation. Now at x is equal to, n is equal to 2, that is for second derivative is to be evaluated. So second order polynomial we want to use. Second derivative is evaluated, so first derivative f dash of x was minus 0.4 x to the power of 3 minus 0.45 x square minus 1.0 x minus 0.25. so second derivative f double dash of x is nothing but minus 1.2 x square, differentiating above polynomial with respect to x, so 3 into 4, 12, that is 1.2 minus 0.9 x minus 1.0. so this is second order derivative f double dash of 0. if we substitute, so this term becomes 0, this term becomes 0, answer will be minus 1.0. so now to find out second order approximation, therefore the second order approximation is given by f of xi plus 1 is approximately equal to f of xi plus of f dash of xi into h plus of f double dash of xi divided by 2 factorial h square. So this was 0th order, this was first order, now second order we are going to consider. So f of xi, value which we obtained, if xi is 0, so this is 1.2. So f of 0 is 1.2. Then f dash of 0 was f dash of 0 was minus 0.25, minus 0.25, and f double dash of 0 is just, we have seen here, it was 1.0 minus 1.0. By substituting these terms, minus 0.25, h value is 1, minus of 1 into 1 square, h value is 1, divided by 2 factorial is 2. So on simplification, this gives us f of xi plus 1, that is nothing but f of 1, is equal to 0.4. This is f of 1 is equal to 0.45. So true error is equal to, the true value is 0.2, and answer which we obtained here is 0.45, minus 0.45. So error works out to be minus 0.25. So error is going to decrease. If you see, in first case it was large, then second case it has reduced, and now it is again reduced. So now for n is equal to 3, now the third order or third derivative is estimated at xi is equal to 0. So f triple dash of xi is given by, now if we differentiate this, f triple dash of x is equal to minus 2 into 1.2, 2.4x minus 0.9, minus 2.4x x minus 0.9, minus 0.9. Now f triple dash of 0 gives us minus 0.9. So f triple dash of 0 is minus 0.9. Now third order approximation, therefore the third order approximation is given as f of xi plus 1 is approximately equal to f of xi plus of f dash of xi into h plus f double dash of xi into h divided by 2 factorial plus f triple dash of xi into, so this is square, h to the power of 3 divided by 3 factorial. So now this is equal to f of xi, that is f of xi which is 1.2 minus of f dash of xi is minus 0.25 into h value is 1 plus of f double dash of xi is minus 1.0 into h square, h value is 1 divided by 2 factorial. 2 factorial is 2 plus of, sorry, so f triple dash of xi is minus 0.9 into h value is 1 to the power of 3 is 1, 3 factorial is 6. So on simplification we get this as 0.3, f of 1 is equal to 0.3. Now true error is equal to 0.2 is true value and approximate value which we obtained is 0.3, so error is minus 0.1. So if you see at every stage this error is going to get reduced. So earlier error was minus 0.25, prior to that error was minus 0.75, prior to that error was 1, minus 1. So now this error has reduced significantly, we can see it is minus 0.1. So this is at third order approximation. So as we take higher order, so this error will get reduced. So in zeroth order error was larger, in first order error was less, then gradually error has reduced. Now at n is equal to 4, at fourth order, the fourth order derivative is estimated f fourth of xi. So if you take fourth derivative of this, if you differentiate this term, so differentiation of this is f fourth of xi will be only minus 0.9, sorry, will be minus 2.4. So if you substitute x is equal to 0, then also it will be f fourth of 0 will be minus 2.4. So fourth order derivative is minus 2.4. So now here it is minus 2.4. Now we can find out fourth order approximation. Therefore the fourth order approximation is given as f of xi plus 1 is approximately equal to f of xi plus of f dash of xi into h divided by 1 factorial plus f double dash of xi h square divided by 2 factorial plus f triple dash of xi h cube divided by 3 factorial plus f4 of xi h to the power of 4 divided by 4 factorial. So now f of xi is 1.2. If we see f dash of 0 is minus 0.25 minus 0.25 into h value is 1 divided by 1 factorial is 1 minus f double dash of xi. F double dash of xi is minus 1 minus 1.0 into 1 square divided by 2 factorial is 2 minus f triple dash. F triple dash is minus 0.9 into h value is 1 divided by 3 factorial is 6 minus this f fourth of xi, just we obtained it as minus 0.245 minus 2.4 into h value is 1, 4 factorial, that is 4 into 3 12, 12 into 2 24. So on simplification we get it as .2, and the remainder term Rn is going to become 0 because fifth order derivative of x becomes 0. So remainder term becomes 0, fifth order derivative is going to become 0, that is n plus 1. So therefore, thus the fifth derivative of fourth order polynomial is 0, therefore R4 is equal to 0. So Rn means R4 is 0. Now error, if you see true error, so true value is 0.2 and approximate value which we have obtained is 0.2, so error is 0. So if we take fourth order polynomial or fourth order Taylor's approximation polynomial, then we are going to get the approximate value as that of true value and error becomes 0. So the higher is the approximation, lowest is the error. So in this way error can be reduced. So the Taylor series expansion to the fourth derivative yields an exact estimate of xi plus 1 is equal to 1. So if we substitute f of xi plus 1 as f of 1, so value of this is 0.2, and by approximation using Taylor series we are going to get f of xi plus 1 as 0.2. So this is how we are going to use Taylor's approximation polynomial for finding approximate values of function in the interval. If we know the value of function at xi, and to find out function value at xi plus 1, we can use Taylor series, and using Taylor series the approximate values at f of xi plus 1 can be determined. So today we stop here. Tomorrow we will continue with the rest of the things. Error propagation and functions of a single variable we will discuss in next class. Thank you.